Welcome to Measurement Lecture B. Today we're going to start off with learning about significant figures. I'm not sure if they try to teach you this in the middle school. Some teachers do, some teachers don't, but nonetheless here we are in chem. We have to know about significant figures. So if I look at a number like 47.0020, sometimes I need to be able to count how many significant figures are present in that measurement. So let's say it's that many liters. I need to know how many significant figures are in that measurement, and so today we're going to learn how to count them, and then soon we're going to learn where those significant figures are born. So any digit or integer or figure inside that measurement that is not a zero is automatically significant, as you see here. So anything that's a 1, 2, 3, 4, 5, 6, 7, 8, or 9 is automatically significant. So if I were to look at this value, I know that the 4 is significant, the 7 is significant, and the 2 is significant. So now we need to address anything that's not a zero. Zeros can come in a bunch of different places. It can come at the beginning of a measurement, in the middle of a measurement, or at the end of a measurement. In the example above, I did not have any leading zeros. A leading zero might look like this, 0.04. So these two zeros out in front, even though one is before the decimal and one is after the decimal, they are both considered leading zeros and they are never significant. Never significant. So this value of 0.04, because the 4 is significant, it would be said to have one significant figure. So there's our leading zeros, never significant. If I have zeros in the middle of a measurement, we'll call those captive. As you can see here, the 7 is significant, and the 2 is significant in the value up above. And the zeros in between, I like to think that they're being held captive. So as such, they're sandwiched in between. They are both considered to be significant. So that is captive zeros or zeros in the middle. Now we have to look at zeros at the end of a value. Zeros at the end of a value, we call those trailing zeros. And of course, at the end, it depends. So we see that our 0 here is at the end. So we have to take a look. You pick your head up and you look. Oh, look, there is a physical decimal point right there. So if you see a physical decimal point, those zeros are significant. So that means this trailing 0 is significant, and the value up here is going to have a grand total of 6 significant figures. Whereas if I didn't see a decimal point, then that 0 at the end would not be significant. So let me talk about writing the value 50. I can write the value 50 like this, or like this, or of course in Crazy Chem you can write it like this. And what's the difference between the three? The difference between the three is whether I see a decimal point or not. In this first value for 50, there is only one significant figure because my trailing 0 does not display a decimal. My second value that I wrote for 50 has actually 3 significant figures. Both of these zeros at the end are considered trailing, and so therefore, because I see a decimal, they are both significant. Now, only in analytical science class like chem or physics will you see a value like 50 written like this. Here the reader wants to tell you with very, very, very much emphasis that this value needs to have 2 significant figures. Again, my 0 at the end is trailing, but it is significant because I do see a decimal point. So let's take a look at some practice. If I look at the value 101.02 and I just consider the zeros, both of these zeros are considered to be captive. So this has a total of 5 significant figures. This guy is supposed to be written like this, I think, to have 3. If I write it like 20.0, then this guy is going to have 3 significant figures. My next guy along the way, I can see that I have zeros in the front here. All three of those zeros are considered to be leading. They are not significant, but this 5, this 3, and this 2 are significant, and this 0 is also significant because it's captive. So truth be told, this value had leading and captive zeros for a total of 4 significant figures. This last guy, second guy to the last guy, 17,000. I can see, of course, my 1 is significant, my 7 is significant, and these trailing zeros are not significant because there's no decimal place. So 17,000, even though I wrote down 5 digits, only 2 of them are considered to be significant. So this one's a rough one right there. The last value, back to something a little easier, trailing with the decimal place, all 4 of those are significant, so piece of cake there. If we wanted to make sure all of these values contained 3 significant figures, now we need to incorporate a little bit of rounding. So what you can do is put a box around 3 significant figures and look to the next value. So 761.5, because of that 5, the 1 would round up to a 2, and this would be 762. Here again, box around 3, the 3 does not round up, so that's 14.3. Box around 3, the 4 does not round up, 10.4. Box around 3, the 7 is going to round up to 8, so I just leave it at 108? No way. Let's say I owe you $10,789 and I tell you I'm going to pay you to 3 significant figures, and I'm only going to pay you $108. There's a little bit of a problem with that in the fact that, yes, we have to have 3 significant figures, but if I do like this, these trailing zeros here are not significant, and I still am able to maintain my order of magnitude. Same trick here. If I look at 802, this 4 does not round up, 802, and I need to maintain the 0 to make sure I'm in the thousands place. Back to easy, this guy is 204. This already has 7, oh, I'm sorry, these are all the answers, so there we go. So we get a good idea of where all those guys came from. Now, why do we have to count significant figures? We have to count significant figures because they are born with measuring devices. If I consider some of the measuring devices that we might use in the lab, here I have a 100 milliliter graduated cylinder, and here I have a 10 milliliter graduated cylinder. You can see they're both about the same height, so it would stand to reason that the 10 milliliter graduated cylinder is more accurate. It holds more stuff. I'm sorry, it holds less stuff, but it's the same height, so we're going to be able to take a closer look at that column of liquid. If I look at this 100 milliliter graduated cylinder, I can see that it's numbered by 10s. If I look at the 10 milliliter graduated cylinder, it's numbered by 1s, but it also has 10 equal divisions in between. So the general rule for using significant figures with a measuring device is you're going to write down all the digits that you know for sure, plus you are allowed to estimate 1 digit. So let's examine this 100 milliliter graduated cylinder on the left. Of course, you know you read from the bottom of the meniscus, so here we go. I want to say that I know the tens place for sure. It's between 60 and 70. So I write down a 6 for the tens place. And what I can see is it's maybe halfway, maybe a little less than halfway, but that's the best I can do. So if I write down 65, no one's going to chop my arm off over that. If I write down 64, no one's going to chop my arm over that, because this ones place is going to be my 1 estimated digit. So this is the one we know for sure, and this is the one that we estimated. So now let's consider our 10 milliliter graduated cylinder. If I take a look again at that same rule, I'm going to write down all the digits I know for sure. I know for sure the value is between 5 and 6, so I'm going to write down a 5 for the ones place. No problem there. Now we're going to look at this close-up view here, and we can see that the tenths place is actually delineated. There's 10 equal divisions in between. So as I count them, 1, 2, 3, 4, I want to say it's between 4 and 5. So I've got 5.4, I know that for sure, and I want to say it's about halfway between 5.4 and 5.5, so my estimated digit is going to be that halfway point, and I'll call that a 5 because that's halfway. So I knew my ones place for sure, I knew my tenths place for sure, and I estimated my 100ths place. Again, this unit is milliliters. So now if we go back to counting our significant figures, we can see that the 100 milliliter graduated cylinder on the left enables us to have 2 significant figures, whereas the one on the right enables us to have 3 significant figures. And then that's going to come into play when we start doing math with these measurements. So, same thing, having a look at our thermometer on the left and the right, they are exactly the same. And we can see that this thermometer is numbered by tens. So I know the tens place for sure. My value is between 40 and 50. So I'm going to write down a 4 for the tens place. And I've got 10 equal divisions in between. So I know those guys for sure. My 10 equal divisions in between, I'm going to start counting those guys up, and it looks like it's better than 7 but less than 8. Again, judge me, I've got bad eyes, but better than 7, less than 8. So I know my ones place there for sure is a 7, and I have to estimate my tenths place. So if you ask me, I don't know, it might look like it's pretty darn close to 48, so I might be willing to call that 47.7. And that is the digit that I know for sure. This is a digit I know for sure, and this is one that I estimated. So this temperature value of 47.7 degrees Celsius has 3 significant figures. Again, 2 that I know for sure and 1 that's estimated. So now we said at one point in time we're going to be asked to do some math with significant figures. And so therefore, let me show you how that's going to come about. When we have to do math, we come in, there's 2 classifications for that. We're either going to have to multiply and divide or add and subtract. So if we are adding and subtracting, we don't even have to consider significant figures per se. All I have to do is have a look at places after the decimal. So if I look at this example, if I'm taking 4.8 and I have to subtract 3.965, 4.8 is my value with the least number of decimal places. So I push the buttons in the calculator, give myself a screen dump right there, but then I have to fix it. And I realize that once I push my buttons on my calculator, I'm only allowed to have 1 decimal place. This value that was born with some kind of measuring device only had 1 decimal place. The second value was measured with a better measuring device, so it has 3 decimal places. So therefore, my final answer is only allowed to have that 1 decimal place. I am limited due to that least accurate measuring device. So again, I draw a wall after 1 decimal place and take a look 1 place further. The 3 doesn't round up, so therefore my value there ends up being 0.8. Taking a look at multiplying and dividing. Now is when we actually have to count actual significant figures. If I have a value like here in my numerator that has 3 significant figures, hopefully you can confirm that the bottom number has 4 significant figures because that 0 is trailing, but you see a decimal place. If I have 3 significant figures and 4 significant figures, my final answer can only have 3. Again, I'm limited to the least number of significant figures. So whatever your calculator, when you push it into your calculator, you do a screen dump, put a wall around 3 significant figures, and then round. If you round up or if you truncate, it doesn't really matter as long as you end up at 3 significant figures. Now let's take a look at graphing. You might remember having to do some graphs in biology. Biology or human body systems or biomedical, hopefully they had you do some graphs. This particular graph came off from a Regents exam in biology, and this one was asking students to do a graph of time versus length of root tips, but they wanted to compare two different sets of data. So you can see here there's a little bit of a key. So whenever their points were plotted, if you were doing the y-axis as your left-hand column of the data table, you were using a dot to graph the point, and then a little circle went around it for some uncertainty. But if you were using time versus this right-hand column, you would again use a dot to graph it with, but instead of a dot, you'd use a little triangle for uncertainty. And so therefore, you could compare two different trends on the same set of axes. So that comes up sometimes in chem, not a whole lot. I'll have you do it later in the school year. But in chem, if you were to have a look at a chem regents per se, if you decide you want to take the regents, or if I put this kind of question on the test, they very often don't make you do that. You'll see that the x-axis sometimes is already scaled for you, the y-axis is already scaled for you, and I won't go through all of the points, but if we can see there, of course, 50-ish is like 67.9, so it's like kind of in that neighborhood. 10 is sort of in the 74.2 neighborhood, so it's, you know, kind of in this neighborhood. And then the 100 is in kind of 58.9 region, so it's kind of in this neighborhood. And we would again put circles around for uncertainty and connect the graph with a freehand line. And so therefore, that's pretty much as far as graphing goes for chem. There will be some time that we may need to do an actual line and calculate the equation for the line, but that's coming up later on in the school year. Then once we examine our graph, we need to be able to put some vocabulary around the relationship. We can have something referred to as a direct proportionality. And that happens to be, of course, you know, when one goes up, the other goes up. When one goes down, the other goes down. And what that ends up being is, in order to be direct, that's pretty much this gives you the direct. However, the proportionality part comes from the fact that the differences are equally spaced. So if I have equally spaced and I've got that nice straight line or linear graph that goes through the origin, I can then say it's directly proportional. So if I have whatever my x-axis value divided by my y-axis value, I'm always going to get the same value. Or if you will, I'm always going to get a constant. And in chem, of course, chemists can't spell. So very often constants in this manner are depicted by a K, believe it or not. So taking a look at this, of course, here we can see we've got something nice and linear. And then you hear me use that word linear. What linear means is it follows the equation for the line, y equals mx plus b. Welcome back to 8th grade, right? So of course you know y is your rise and x is your run, and of course rise over run gives you the slope. So your y-axis value is going to equal your slope times your x-axis value plus b, which is your y-intercept, and in this case your y-intercept is where you go through the y value if you were to extend the line, and you can see here in this particular example the y-intercept is 0. If we have something that's inversely proportional, if I multiply one quantity by the other, like say for example I take the x-axis value times the y-axis value, I'm going to always get that same number. Again, it's always going to be constant, and again in chem we love that K right there. So as one goes up, the other one goes down, and the shape of this graph is no longer linear. Instead, it's going to be hyperbolic. You've got an inverse relationship here. It's an inverse exponential relationship, so therefore you get that crazy hyperbolic graph. Later in the school year, this kind of relationships is going to be important when we start talking about pressure of a gas versus volume. If you think about it just in your head, pressure means squashing. So if I have a gas and I squash it hard, I might have a high pressure. And what you notice is going to happen to the volume because I squashed it hard, it's going to get a low volume. So those two relationships between pressure and volume, they tend to be inverse. And again, as we said, when I multiply those values together, I get that constant K. Switching gears to something referred to as percent error, you're going to find this equation for your viewing pleasure in reference table T. But I have a feeling you probably already know a lot about percent error because you had to do it back in the day, probably back in earth science. So the only thing is the application as it refers to chemistry, percent error becomes difficult. You're like, how could that possibly be difficult? We did that in 8th grade. It becomes difficult when you start involving significant figures, because if you look at the numerator, measured value minus accepted value, you can see that it involves subtraction. And again, if we talk about significant figures, subtraction, I have to consider decimal places when I look at significant figures. But then after I subtract, I have to divide, and dividing uses a different set of rules for significant figures. Dividing, you have to count actual significant figures. So it can become a little bit dicey as far as it goes. Then your third step is to multiply by 100. Now here's the thing. This 100 is the literal definition of percent. If you are speaking the Greek language, they don't even have the word percent. Instead, they just say it's 75 out of 100. So it's automatically assumed percent has to be out of 100. And it's not just maybe close to 100. These two digits aren't estimated. It's exactly 100. It's like 100.000000. I could go on forever. And once I do, check it out. With that decimal place, all of these zeros are significant. So we might say that this 100 is infinitely significant. So therefore, that 100 is not going to count when we talk about percent error with significant figures. So you need to be aware of that. So here's some advice for you. As we said, after we subtract, we are examining decimal places. After we divide, we're examining total significant figures, and we said the 100 does not count for the reason why I already told you. So, to wrap up Lecture B, let's do a practice problem. We want to find our percent error. So we know we've got the formula for percent error, and as it's all fancy in table T, it's measured value minus accepted value. What I like to call that is measured value means you're the student. It is your answer. You measured it. Minus the accepted value. I like to call that the right answer. Yep, okay, so that assumes that your answer is not the right answer. If your answer was the right answer, you'd have 0% error. Divided by the right answer times 100. So as we see here in my setup, my student's value for density is 1.40 grams per milliliter. And the correct answer, or if you will, the accepted value is 1.36 grams per milliliter. So now I'm going to finish my setup. My right answer goes in the denominator, 1.36 grams per milliliter, and carry down my times 100. So I wrote the formula, I showed my setup with my units, and now I need to talk about my answer a little bit. Now let's talk about my numerator first. I have 1.40 minus 1.36. So I'm going to grab my handy dandy calculator here and take a look at how that turns out. 1.40 minus 1.36. Calculator says in a screen dump 0.04. Now does that mean I can record 0.04 there? And if you said yes, you were right, because 1.40 has 2 decimal places. So therefore, I've got 2 decimal places here. And this guy has 2 decimal places here. So 0.04 has 2 decimal places, so therefore I'm allowed to go ahead and let that go. Of course, my units are grams per milliliter. Grams per milliliter minus grams per milliliter is going to give me grams per milliliter. So now let me continue on with the rest of my problem. The rest of my problem, I still have to divide by 1.36. And I have to multiply by 100. Now, truth be told, I can do that all in one shot on my calculator, simply because multiplying and dividing use the same set of rules for significant figures. So my 0.04 divided by 1.36 times 100, and calculator says 2.9411767. And of course we know the units are percent. Now let's kind of back up the truck here a little bit with regards to units. If you notice here, after I subtracted, my numerator's units are actually grams per milliliter. My denominator's units are also grams per milliliter. And what happens if I take grams per milliliter divided by grams per milliliter? Both of those units cancel. So you can see that after that division, I have a unitless quantity. But by multiplying by 100, it allows me to put the percent value at the end. So that ends up being my unit by default. So clearly my screen dump is not correct for the correct number of significant figures. Now that we divided, we have to examine our significant figures again. 0.04 has in it one decimal place. So yikes. It has a one significant figure due to the two decimal places, but it has one significant figure. So I have to be mindful of the fact that there is one significant figure in my numerator, and I have three significant figures in my denominator, and we said the 100 does not count. Doesn't count. So therefore, my answer can only have one significant figure. So I'm going to put a box around one significant figure, make sure I have the correct order of magnitude, and record the correct value as 3%. I hope you enjoyed Measurement B. Have a good one.